Hello, my name is Alex and I work on developer tools. Today I want to talk to you about the new C++20 features supported in Xcode 14. I will specifically focus on how C++20 concepts simplify and improve the type safety of generic C++ code. I will demonstrate how to use concepts and will explain how to create your own concepts as well. I will end the talk by listing several other new C++20 features supported in Xcode, and will touch on how some of them can be used to improve the performance of your C++ projects through the power of compile-time code evaluation. Before diving into C++ concepts, let's first go over a quick overview of how to write generic code in C++. Let's say I want to write a function that checks if a number is odd. I can write a function that takes in an int parameter, and it would work with any value that can be represented by the int type. What would happen if I pass in a 64-bit unsigned integer value to it? A concrete function like this one does not behave correctly with 64-bit values, as they get truncated to fit into the int type. To fix this, I can make isOdd a function template. Now that I have a function template, I can pass in the 64-bit unsigned integer value to it. The compiler will now automatically generate a specialization of isOdd that works correctly with the uint 64c type. This is really useful as it means I don't have to write two versions of isOdd that operate on two different types. You can use C++ templates to write generic functions like isOdd and generic container classes as well. Let's take a look at how isOdd can be used. This function is tested with several test cases that I added in my test file. Unfortunately, I've made a mistake in one of my tests. The compiler caught the mistake, but instead of pointing to where I made the mistake, the compiler shows an error inside the isOdd template. It looks like I made a typo and wrote out 1.1 in my test instead of 11. Because of that, the compiler generates a specialization of isOdd that takes in a double type. Unfortunately, it took me some time to find this typo, as Xcode didn't point me to the specific location where isOdd was invoked with the incorrect type. Can the language and the compiler help me find mistakes like this faster? Well, in the current example, the requirements for what types are allowed into isOdd are not specified explicitly. There is only a documentation comment that states that I must call isOdd using integer types. Prior to C++20, C++ programmers did not have a good way to specify template requirements when writing generic C++ code. They often had to resort to documentation comments, specific parameter names, or complicated enable if checks when specifying template requirements. Well, as you might have heard, C++20 introduces a new C++ feature called concepts. You can use concepts to validate template requirements in your generic C++ code. Let's take a look at how concepts can help me validate the types that can be passed into isOdd. First, let's go back to the declaration of isOdd. Currently, I use the class keyword to specify that type C that's used by this template can be any type. C++20 allows me to use a concept instead of the class keyword to restrict the set of types that this template can be used with. I can use the integral concept provided by the standard library to restrict this isOdd function template only to the built-in integer types. The compiler will not even try to specialize this function template when C does not satisfy this concept. The integral concept is declared in the C++ standard library, so I need to include the concepts header to use it in my code. Now that I added an integral requirement to the type C in the isOdd function template, the compiler is able to provide a much clearer diagnostic that points directly at where I made the mistake in my tests. Turns out 1.1 is a double, and therefore it does not satisfy the integral concept. The compiler is able to explain this to me with a clear error message that helps me find and fix this typo much quicker than before. In addition to helping me fix the bug, constraining the type passed to is odd gives me the peace of mind that all the test cases that I have for is odd work only with integer types, and that they're actually testing the intended behavior of the algorithm. You can use concepts to declare the intent for which types your templates are meant to be used with. The compiler will then validate the type requirements before your templates are specialized. Let's take a closer look at how concepts can be used and which core concepts are provided by the C++ standard library. The C++ standard library provides a concepts library. It implements a set of core language concepts that you can use to validate the core behavior of a type. You can access this library by including the concepts header in your code. I've already shown how I can use the integral concept in my earlier example. Now, let's take a look at the other concepts provided by this library. This library provides a number of useful core language concepts, like concepts that test if a type is one of the built-in types. For instance, the floating point concept is satisfied by built-in types like float and double. The static assert shown here validates that this is indeed the case. It also provides a lot of other useful core concepts that check if types are constructible, destructible, convertible, or are they the same as another type. For instance, the convertible to concept tests if a type can be converted to another type. And the move constructible concept is satisfied by types that can be constructed directly from another value of the same type. This library also provides several comparison concepts that test if types can be compared to other types. For instance, the equality comparable concept is satisfied by types that have a valid equals equals operator that works with a value of the same type. In addition to concepts mentioned on the slide, this library provides numerous other core language concepts. It also provides concepts that test if a type can be moved or copied. In addition to that, it also provides concepts that check if a type is some callable object. Now that we've looked over the concepts provided to us by the C++ standard library, let's take a look at how concepts can be used to constrain templates. Like I've shown earlier, you can use a concept instead of the class keyword in a template to restrict which types are allowed for this template. In addition to that, you can use a requires clause in a template declaration if you ever need to constrain a type to multiple concepts. Let's take a look at a slightly different example to see how it can be done. Here I have isDefaultValue function template. It returns true if the given value is equal to the default value of its type. I can use two concepts from the standard library to test that this type supports these operations before this template is specialized. I'm going to add the requires clause to restrict the set of types which are allowed for this function template. Let's see which concepts from the concepts library can help me validate the type here. First, the equality comparable concept tests if C can be compared to another value of the same type. Then, the default constructible concept tests if C is a type with a default constructor. The logical AND operator between them instructs the compiler to validate both concepts. This ensures that this function template will only be specialized with supported types. Let's go over what we've learned so far about concepts. You should use concepts to restrict the types which are allowed to be used in your templates. The compiler will then be able to show clearer diagnostics, as the template won't have to be specialized if a type mismatch occurs. You should reuse the concepts from the concepts library if you need to validate some core behavior of a type. you should add the requires clause to your templates when you need to test if types conform to multiple requirements. We've now seen how to use concepts in C++ programs. C++ allows us to declare custom concepts that validate specific behavior of a type. Let's take a look at how to create our own concepts that validate specific type behavior. Before we do that, though, we need to take a look at how to identify the behavioral requirements that must be validated by the concept we want to declare. I'm going to use a new example to illustrate how to validate specific type behavior using concepts. Say, I'm building a C++ library that can render various two-dimensional shapes to an image. I would like to support various shapes in my library. I'm starting out with a circle shape, as it's the simplest to render. I'm going to use a C++ class to store its properties, like position and radius. In order to render the circle, I'm going to use a distance function-based rendering algorithm that runs on each pixel in the rendered image. This algorithm needs to compute the distance to the shape surface in order to render it. The getDistanceFrom method in the circle class computes it. It returns a negative distance inside the circle and a positive distance outside the circle. In addition to the circle, I would like to render other shapes. For instance, by geometrically subtracting one circle shape from another circle shape, I can render a crescent shape as well. I'm going to represent shapes like crescent that I would like to render using classes as well. Each new shape class includes the getDistanceFrom method. After creating several shape classes, I now would like to try rendering the shapes to verify their implementation. I have a couple of options for how I can create the rendering function that works with any shape. I can create a class hierarchy for the shapes and use a virtual method to compute the distance to the shape surface. However, I'm going to use a function template instead for performance reasons, as I want to avoid the virtual call overhead, as this function is going to be called millions of times during rendering. This is why I created this rendering function template. The computePixelColor function takes in a shape value and checks if the given pixel is inside the shape. If it's inside, it returns a plain white color. This now allows me to verify that shapes can be filled in correctly. This function is a template which makes it work with any shape type, be it a circle, crescent, or any other matching type. Even though a template works well here, I would like to use concepts to constrain the type that can be passed to this function. Constraining the type that's passed to this function will allow the compiler to produce clearer diagnostics when a type mismatch occurs. In addition to that, constraining the type that's passed to this function will also allow me to add additional overloads of this function. In order to constrain the type, I'm going to create a shape concept. This concept will validate the type's behavior and will accept classes like circle, crescent, and any other shape class that I might want to add in the future. In order to create a concept like shape, I first need to identify the requirements that must be validated by this concept. Let's see how this can be done. This function template uses type C as the generic type. An argument named shape of type C is then passed to this function. The shape argument is then used inside the function when I call the getDistanceFrom method on it. As you can see, this is the only requirement I want to validate in my concept, as no other operations are being performed on shape in this function. You can use the requires expression to test if a type behaves in a specific manner. Let's take a look at how I can use requires to create the shape concept. I need to provide a set of expressions that test the behavior of a type inside the requires. I already identified the call to getDistanceFrom as a single requirement I need to test, so now I can go ahead and create the shape concept. I declared the shape concept using the concept keyword. I then added the requires expression to this concept to validate the type. I added an argument list to the requires expression. This argument list allows me to declare a value shape of type C that I will then be testing inside the requires. You can use an argument list in the requires expression to declare values of any type. You will then be able to use these values inside the requires. The body of the requires expression contains a set of requirements it must pass in order for this concept to be satisfied. The shape concept has just one simple expression requirement that checks whether a method call to getDistanceFrom is valid. This expression isn't actually going to be executed in the program. It's only needed at compile time to validate the type's behavior, and it's discarded after the validation. You can use expression requirements to validate the type's behavior by testing if a particular expression compiles or not. This particular expression is not yet complete though, as we are missing the arguments to the getDistanceFrom method call. I know that I want this method to take two values of type float, so I can use two floating point literals to complete this expression. I'm going to add an additional check to test that getDistanceFrom method returns a float value, as that's what is being assumed by my generic code. I'm currently using a simple expression requirement to test if the type has the getDistanceFrom method. However, I can use a compound requirement instead of the expression requirement to test that it returns a float value. The arrow operator can follow a compound requirement. The arrow operator expects a constraint on its right-hand side, so this is where I can use a standard library concept like same as to validate that the call to getDistanceFrom method returns a float value. Now this concept looks ready to me. I can go ahead and use it to constrain the types that can be passed to my computePixelColor function. Now my generic computePixelColor function will only work with types that satisfy the shape concept. This means that classes like circle and crescent will be rendered using this particular generic computePixelColor function, as both of these types satisfy the shape concept. After seeing the plane shapes rendered, I would like to create a different version of computePixelColor that adds colors to some of my shapes. Let's say I want to add a colorful gradient circle class to my shape library. I now need a new function to compute the pixel color in the image. C++20 allows me to create multiple variants of the computePixelColor function template. Each variant must be constrained using different concepts. I'm going to create a new gradient shape concept that will be satisfied by classes like gradient circle. This concept will then constrain a new variant of computePixelColor that only works with shapes that have a gradient. This concept is implemented using a requires expression, just like the shape concept. However, since I want gradient shape to satisfy the original shape concept as well, I include it as the first requirement in the new concept. This ensures that a class that satisfies the gradient shape concept also satisfies the shape concept, which means I can still call the getDistanceFrom method for values of such class. I then use the logical AND operator and the requires expression to ensure that the gradient shape concept can only be satisfied by classes that have the getGradientColor method. Now that I have created the gradient shape concept, I can go ahead and create a new variant of computePixelColor. This function template only works with shape classes with a gradient, like the gradient circle class, as it is constrained by the gradient shape concept. Now that I have all the pieces in place, I can go ahead and try rendering a circle with a gradient. Here, I'm rendering a gradient circle. Let's see which overload of computePixelColor the compiler is going to pick inside the render function. Even though gradient circle can be safely used with both variants of compute pixel color, the compiler picks the overload that is constrained with the gradient shape concept, as it's more specific than the first overload. Because the compiler picks the most matching overload of compute pixel color, I can see this beautiful gradient circle rendered when I test my library. Amazing! Now, let's go over what we've learned about creating concepts. You can create concepts by identifying the behavioral requirements in your existing generic code. You should use the requires expression to create concepts to validate the behavior of types. You can also use concepts to create more specific variants of generic functions and classes. We've now seen how to enhance your generic C++ code with concepts. In addition to supporting concepts, Xcode 14 has improved its support for other C++20 features as well. More specifically, I would like to highlight the improved support for compile-time C++ code evaluation in Xcode 14. Compile-time code evaluation is useful as it can reduce the cost of initialization of variables in your C++ code. This could help reduce your app launch time if your app has a lot of C++ code that depends on complex initialization sequences. In addition to that, compile-time code evaluation can help you validate constants that require validation at compile time. This could help you catch bugs before your code even runs. Let's take a look at an example to see how I can use compile-time code evaluation in C++. Here, I have a snippet of code that initializes a color palette in my shape rendering library. This library is then used in an iOS app that renders the shapes to the display. Each color in the palette is initialized by parsing a string literal with the HTML hex code of the color. Currently, the from hex code function needs to parse 3 string literals during the initialization of the array. Complicated constant initialization operations like this one can have a measurable impact on the launch time of my app if I have a lot of them. I can use compile-time code evaluation to ensure that this array is initialized with constant color values instead. Let me show you how this can be done. The constexpr keyword enables compile-time code evaluation in C++. I must add it in several places in my example in order to ensure that the palette is a constant color array. First, I need to add the constexpr keyword to the from hex code function. The compiler will now be able to execute the code in this function at compile time when it's used in the compile time initialization sequence. You should make your C++ functions constexpr when you want them to be evaluatable at compile time. The compiler will let you know if the code in such function cannot be evaluated at compile time by showing an error when you use it in a constexpr initialization sequence. However, you can also examine a function before adding constexpr to see if it can be evaluated at compile time. Let's take a peek into from hex code to see how to check if a function like this one can be a good candidate for compile time code evaluation. This function uses a number of language constructs, like if statements, and primitive operations like comparison operators and arithmetic operators. All of these operations can be evaluated at compile time. Also, this function makes several calls to another function, hex to int. I have already annotated hex to int function with constexpr, so calls to this function can be evaluated at compile time. Overall, it looks like from hex code contains code that the compiler should be able to evaluate at compile time. So I think it's safe to proceed and use it in a compile time initialization sequence. After making sure that from hex code can be evaluated at compile time, I then need to add the constexpr keyword to the color palette variable declaration. The compiler now guarantees that it will evaluate the entire initialization sequence for this array at compile time. More specifically, the compiler will evaluate each call to the from hex code function. the evaluation will produce a constant color value that will replace the original call to the function in the palette's initializer. Since all the calls to from hex code are now replaced by constant color values, the color palette variable is now guaranteed to be initialized by an array literal that contains constant color values. This means that now my app doesn't have to pay additional cost for parsing the color values when this palette is initialized. This is great for the launch time of my app, as it reduces the amount of work this C++ library inside the app has to do at startup. You should make your C++ variables constexpr when you want to ensure that they're initialized with constant values. Xcode 14 has actually greatly improved its standard library support for compile time evaluation. This year, we've added the constexpr support to several different standard library types and algorithms, which can now be used during compile time code evaluation. In addition to that, Xcode 14 has greatly improved its C++20 standard support. All of the features shown here can now be used in C++20 mode. You should switch to C++20 mode today if you haven't already done so. You can use the C++ language dialect setting in your Xcode project to upgrade to C++20. Switching to C++20 will let you use features like concepts in your code. C++20 does not require a minimum deployment target, so you can still ship your code for the same OS version that you are currently targeting. Try C++20 today. Thank you. Enjoy the rest of the developers conference.